Hello and welcome to Astronomy Daily. Give us 10 minutes and we'll give you the universe. I'm Anna, and with me, as always, is my co-host Avery. Hey Avery, it's January 5th, 2026. Hope everyone's having a fantastic start to the year. We've already seen some exciting launches and sky events kicking off, and I'm pumped for what's ahead.
Hi Anna, and a big hello to all our listeners out there exploring the cosmos with us. Absolutely, 2026 is buzzing right from the get-go. Today, we've lined up 6 intriguing stories, from cutting-edge tech for satellites hugging Earth closer than ever before, to a mission finally orbiting the scorched world of Mercury, black holes confirming Einstein's wild predictions, a speedy SpaceX launch, NASA's clever waiting game for Mars probes, and the sharpest X-ray peek yet at a spinning black hole beast. We'll dive deep, discuss the science, and share our thoughts. Let's jump in.
First story of the day is all about pushing the boundaries of satellite orbits. We're talking about very low Earth orbit, or VLEO satellites, which zip around at altitudes between 100 and 400 kilometers above Earth. That's a lot closer than the usual low Earth orbit stuff, which can go up to 2,000 kilometers. Avery, why go so low, and what makes this the next frontier?
Great question, Anna. The advantages are pretty compelling. At these lower heights, satellites can capture much sharper images for Earth observation. Imagine super detailed views that boost agriculture by spotting crop health issues early, enhance climate monitoring with precise data on deforestation or ice melt, aid in disaster response like tracking wildfires or floods in real time, and even support military reconnaissance with crystal clear intel. On the communication side, the lower altitude means reduced signal latency. Think faster internet and more responsive networks. Weather forecasting gets an upgrade too, with better resolution on cloud formations and atmospheric layers.
Sounds revolutionary, but I bet there are challenges. The atmosphere doesn't just vanish at 100 kilometers. There's still enough air to cause serious drag, right? Satellites could spiral down and burn up in mere days without some kind of constant boost.
Spot on. Atmospheric drag is the big hurdle, along with corrosion from atomic oxygen. That's highly reactive stuff that eats away at materials, and intense heating from friction pushing temperatures beyond 1,500 degrees Celsius. To combat this, engineers are developing innovative propulsion systems, like air-breathing electric thrusters. These scoop up sparse atmospheric molecules and ionize them for thrust. For example, researchers at Penn State are experimenting with microwave plasma technology, while DARPA's Otter program, partnered with Redwire, is testing similar concepts. It's like giving satellites a way to breathe the air they're flying through.
And with orbits like LEO getting increasingly congested, Starlink has over 6,000 satellites alone, plus competitors. VLEO could open up new real estate in space, reducing collision risks up higher. Investments are skyrocketing, with projections in the hundreds of billions over the coming decade. Right now, it's mostly prototypes and demos, but companies like Earth Observant and Albedo are leading the charge. This could really change how we monitor our planet and connect globally.
No doubt. It's exciting to think about the applications. Closer orbits mean better data, and who knows what breakthrough that'll lead to in environmental science or urban planning.
Moving on to our second story, after a long journey, the Bepi-Colombo mission is poised to enter orbit around Mercury later this year, in the second half of 2026. This is a collaborative effort between the European Space Agency, ESA, and Japan Aerospace Exploration Agency, JAXA, launched way back in October 2018. It features 2 orbiters: ESA's Mercury Planetary Orbiter, focused on the planet's surface, composition, and interior structure, and JAXA's MEO, which will study the magnetic field, magnetosphere, and thin exosphere.
Mercury is one of the trickiest planets to reach because of its proximity to the Sun. The gravity pull is immense, so you need a lot of energy to slow down and get captured into orbit. Bepi-Colombo has been using a series of gravity assist flybys, Earth once, Venus twice, and Mercury itself 6 times to bleed off speed without guzzling fuel. The planet's extreme environment adds to the challenge. Surface temperature swings from negative 173 degrees Celsius at night to 427 degrees Celsius during the day. It has an eccentric orbit, a massive iron core making up 60% of its mass, and a surprisingly active magnetic field despite its small size.
Once in orbit, it'll provide groundbreaking data, like the first ever X-ray fluorescence maps of another planet's surface. That'll reveal elemental compositions, things like magnesium, aluminum, silicon, in unprecedented detail, helping us understand Mercury's volcanic history and crustal evolution. We'll also get better insights into its tenuous atmosphere and how solar wind interacts with the magnetosphere.
Comparing this to data from Earth, Mars, and the Moon will refine our models of inner solar system planet formation. The instruments are state-of-the-art, but after 8 years in space, the teams will be holding their breath during activation. If all goes well, it'll operate for at least a year with possible extensions.
I'm eager for those close-up views and what they tell us about the sun's closest companion. It's been a patient wait, but science like this is worth it.
Absolutely. Now, for something that bends the mind and space-time itself. Astronomers have caught a black hole in the act of twisting the fabric of reality, exactly as Albert Einstein predicted back in 1918 with his general theory of relativity. This is the lens-theoring effect, also known as frame dragging, where a spinning massive object warps space-time around it.
The observation comes from a tidal disruption event dubbed AT 2020 AFHD, where a supermassive black hole shredded a passing star, creating a swirling accretion disk of hot gas and launching powerful jets. Using X-ray data from NASA's Neil Gerald Swift Observatory and radio observations from the Very Large Array in New Mexico, the team detected the disk and one jet precessing, or wobbling, in unison every 20 days. That wobble is the direct result of the black hole's spin dragging space-time like a vortex.
These events are rare. Tidal disruptions happen maybe once in every 10,000 to 100,000 years per galaxy, and catching the repeating signals needed for this measurement is even tougher. It not only confirms general relativity in one of the most extreme environments, but also gives us a new tool to precisely measure black hole spins. Understanding spin helps explain how these monsters power jets that can stretch across galaxies and influence star formation.
It's incredible. Einstein's equations, scribbled over a century ago, still hold up under scrutiny from modern telescopes. This could lead to more detections as we get better at spotting these quasi-periodic eruptions.
On to launches, SpaceX is keeping the momentum from 2025. Just yesterday, on January 4th at 1:48 a.m. Eastern Time, they sent up a fresh Falcon 9 from Space Launch Complex 40 at Cape Canaveral Space Force Station for the Starlink Group 688 mission.
The rocket carried 29 next-gen Starlink satellites into low Earth orbit, deploying them successfully about an hour after liftoff. This was the debut for booster B-1081, which nailed its landing on the drone ship. Just read the instructions in the Atlantic. These satellites are part of the expanding constellation aimed at global broadband coverage, with improvements in speed and coverage.
This marks SpaceX's second launch of 2026 already, following closely after their first one earlier in the week. With over 165 launches last year, they're on track to beat that record. The reliability of Falcon 9 continues to impress, enabling more frequent and affordable access to space.
Indeed, it's democratizing orbit in ways we couldn't imagine a decade ago.
Our fifth story involves a bit of cosmic patience. NASA's Escapade mission to Mars. The twin probes, named Blue and Gold for Escape and Plasma Acceleration and Dynamics Explorers, blasted off aboard Blue Origin's New Glenn rocket in November 2025.
Their goal is to investigate how the solar wind erodes Mars's atmosphere, a process that stripped away much of the planet's air over 4 billion years, turning it from potentially habitable to the barren world we see today. By measuring plasma flows, magnetic fields, and ion escape rates from 2 vantage points, they'll provide a 3D view of this interaction.
But here's the twist. They're not rushing straight to Mars. Due to planetary alignment at launch, they're spending about a year in a halo orbit around Earth's Lagrange point 2, roughly a million miles away on the far side from the Sun. This stable, kidney bean-shaped path conserves fuel while waiting for the optimal window.
In fall 2026, they'll ignite their thrusters for a trajectory adjustment, using Earth's gravity for a slingshot to Mars, arriving in September 2027. Science operations kick off shortly after, lasting at least a year. The dual probe setup adds redundancy. If one fails, the other can still deliver key data.
This flexible design expands launch opportunities beyond the every 26 months home and transfer windows, making Mars missions more feasible. It's a smart blend of orbital mechanics and engineering.
Patience in space pays dividends. Reminds me of how Voyager probes are still going strong after decades.
Last but not least, the X-ray Imaging and Spectroscopy Mission, or XRISM, has given us the clearest X-ray spectrum yet of a fast-spinning supermassive black hole in the active galaxy MCG-6-30-15, located 121 million light-years away in the constellation Aquarius.
This black hole, weighing in at about 2 million solar masses, is accreting material at a furious pace. XRISM's Resolve spectrometer captured a broad asymmetric iron K alpha emission line, distorted by relativistic effects near the event horizon, where gas orbits at nearly light speed. By combining this with archival data from ESA's XMM Newton and NASA's NuSTAR, astronomers dissected the spectrum into components from the inner accretion disk and outer regions.
They identified 5 distinct zones in an outflowing wind, plus a hot corona above the disk. Remarkably, the reflection signal from gas perilously close to the black hole is 50 times brighter than from distant material, confirming the hole's high spin rate, likely close to the maximum allowed by physics. This spin influences how efficiently black holes accrete mass and eject jets.
These insights help unravel how supermassive black holes co-evolve with their host galaxies, whether through steady accretion or violent mergers. XRISM, a JAXA-NASA collaboration with ESA input, is setting new standards in high-energy astrophysics with its microcalorimeter technology.
It's transforming our view of the hot and energetic universe, one spectrum at a time.
Wow, what an episode packed with innovation, discovery, and cosmic wonders. From VLEO sats redefining Earth observation to XRISM's black hole revelations, it's a thrilling time to be following space news.
Couldn't agree more. Thanks for tuning in to Astronomy Daily. We love sharing these stories with you. If you're enjoying the show, please subscribe, leave a review, or tell a friend. It helps us grow and reach more stargazers.
We'll catch you tomorrow with the latest updates. Until then, keep wondering about the universe.
Clear skies, everyone.
Astronomy.